Okay, so we are doing homework 2. I didn't realize it was going to be due so soon, but given the weather and whatnot, we had to shuffle stuff around, and so he moved up, or I guess homework 2 seems to be coming up rapidly approaching. So there's a lot to do. This video will probably be broken into 2 pieces and 2 parts. So if you've signed up and are watching this video now, don't worry, you will get the second part later on. It might not be today, but it might be in a couple days. And I'll try and make sure that whatever 30, 45 minutes I need to record so that the last few problems get sent to you, I will make sure is done soon. A few other things. My solutions will not be very heavily derivation based, where I use a lot of calculus and formulas, or at least a lot of calculus, I should say. So as you recall, in the last homework, we very often use some sort of function we wanted to maximize subject to some constraint G, and we use this Lagrangian function to derive those maxima minima. I'm not going to do that as much here because I've been informed by a student that the professor himself has stated that shortcuts are encouraged. So we will not be using Lagrangian as much, and we will be relying on known results from a cheat sheet that I provided to you. So we're going to rely on those, and it will make your homework a lot easier than if we were just to do a lot of calculus all the way through. So I recommend having that cheat sheet out. If you're watching this video, pause the video if you have the opportunity to open that cheat sheet and kind of have it open to the side, because I'm going to be using that for a lot of these problems. And as we get started, I'm going to be using it for this very problem, number 1, 4.1, I should say, because this is a Cobb-Douglas production function, or a Cobb-Douglas utility function. So this is Cobb-Douglas. And because it is, I can get very quick answers to optimal values for T and S. So just in case you don't have that open, here's what it looks like, Cobb-Douglas. And you've got a utility function U equals some constant K, usually, times X to some alpha times Y to some beta, where K is usually very often 1. It is in this case. K is 1. And it might not be obvious to you that this is Cobb-Douglas because you see a square root, but the square root can be written as a power of 1/2. So this is T to the 1/2 times S to the 1/2. And basically most of our answers to this problem are sitting right here in this row. So we're going to use that back here on the whiteboard. The first question from this section asks us, if Twinkies cost 10 cents each and soda costs 25 cents per cup, how should Paul spend the $1 his wallet gives him to maximize his utility? So basically, we're told that price of Twinkies is 10 cents. Price of soda is 25 cents. Dollar sign here. 25 cents. And his income is $1. So the question is, how would we allocate his resources, or how would he allocate this $1 in spending on Twinkies and soda so as to maximize this? Again, just to reiterate something I said earlier, I could very well say my Lagrangian is T to the 1/2, S to the 1/2, plus lambda times my budget constraint, which would be 1 minus 0.1 T minus 0.25 S. And I can go about solving this guy the normal way we did for homework 1. But that would be tedious, and we are going to kind of take to heart what the professor has said is use shortcuts if you have them. So here is a shortcut. According to the cheat sheet I've given you, the optimal value for X, or I guess we'll say T star, is equal to alpha times income over price of X, or in this case T, alpha plus beta. So all you need to do is take the values of alpha, beta, I, and the price of T and plug it in, not price of like tea that you might drink, but price of tea for Twinkies, and plug them into this formula. So alpha is 1/2. Alpha and beta are these powers on T and S. So we have 1/2 times 1 over 0.1 times alpha plus beta. And this comes out to be 1/2 times 1 divided by 0.1 would be 5. Similarly, let's go ahead and find the optimal value for soda. That would be beta times I, again, just using the cheat sheet here, divided by the price of Y, but in this case, not Y, but S, because those are the letters we're using here, times alpha plus beta. That would give me 1/2 times 1 divided by 0.25 times alpha plus beta, which is again 1/2 plus 1/2, for a final answer of 2. And so the optimal bundle is, he maximizes, you say Paul maximizes his utility by purchasing 5 Twinkies and 2 sodas, period. Cool, that's it. That's part A. But of course, there's a little bit more to this question. There's part B. Part B says, if the school tries to discourage Twinkie consumption by increasing the price to 40 cents, by how much will Paul's mother have to increase his lunch allowance to provide him the same level of utility he received in Part A? This is an expenditure question. So price of Twinkies have changed. What income would need to be supplied so as to maintain the same level of utility as before? This kind of question is an expenditure function question. So with that in mind, I'm going to be referencing, again, my cheat sheet, which has on it an expenditure function. Expenditure function for Cobb Douglas is unfortunately this monstrosity. So I'm going to kind of copy it into the whiteboard here, or at least I'm going to have to make it so I have to toggle back and forth between these things from time to time because I don't have it memorized myself. But I did derive it. I did derive it by hand. It was just painstaking. Okay, so we have alpha plus beta times price of x to the alpha times price of y to the, well, I shouldn't say x, we'll say t to the alpha, and price of s to the beta to the 1 over alpha plus beta divided by alpha to the alpha times beta to the beta. And I would think that there's probably some utility that I need to put here. So u bar. By the way, some professors use u bar, some professors just use u, some professors even use v. So some people even use lowercase v. But this term here is just some fixed utility that we are trying to achieve. We are going to plug in alpha, beta, pt, and ps accordingly. So we're going to have 1/2 plus 1/2. That gives us 1. Actually, you know what I'm going to do is, to make your life a little easier, I'm going to undo a few things and say, rather than deal with the notion this is going to be alpha plus beta and this is a strange power of 1 over alpha plus beta, in our case, alpha plus beta is 1, right? 1/2 plus 1/2 gives us this 1. So with that in mind, this is 1, this is 1. That means this entire power is 1. So really a lot reduces to just whatever u bar is when we figure that out, times price of t to the 1/2 times price of s to the 1/2 divided by 1/2 to the 1/2 times another 1/2 to the 1/2. A lot of halves flying around here. And now we can kind of plug in what we know. Let's start with the p sub t. P sub t, notice we were told that the price has increased to 40 cents. So Twinkie price has gone up to 0.4 rather than 0.1. So this is the change now for part B. The price of Twinkies is now 40 cents. We have 0.4 to the 1/2 times price of soda still 0.25 to the 1/2. I'm going to simplify this denominator. Don't worry, I'll come back to that u bar term in a second. 1/2 to the 1/2 times 1/2 to the 1/2 is 1/2 to the 1, which is just 1/2. So trust me when I say this entire thing down here simplifies to just 1/2. And then I have this u bar term. The question is, what is this u bar term and where do I find it? U bar is the level of utility that we had before. How do we find it? Oops, that's not a question. This is a question. How do we find it? We take our old values of x and, well, not x and y, but s and t, and plug them into u. So what were our old values of t and s? They were 5 and 2. So if I plug these things into my old utility function, which was square root of t times s, I get square root of 10. 5 times 2, 10. Hopefully that's not too crazy. So I got 10, square root of 10, or you can say 10 to the 1/2 if you'd like to say that instead. So we have 10 to the 1/2 goes here. That's your u bar. All this, when I multiply everything out, I would grab a calculator to multiply all this if you need it. I think you should get 2. So this is the level of income. This is the level of income we would need to be as happy as we were before the price change. Be careful because this means the answer to your question is 1, right? Remember, the question is, by how much should Paul's mother increase his income so as to keep him as happy as he was before? Well, don't forget, he started out at $1. And what we're saying is that to be as happy as he was before, he'll need $2. So how much would his mother need to increase his income? She would have to increase it by $1. Of course, if you just say it increases to 2, there's probably an implication there that it's increased by 1. since he started with $1. But his old income was 1, and it needs to now be 2 with the price change to be as happy as he was before. Are there any questions on 4.1? Because that's pretty much everything. And I'm going to clear all this and then go on to the next one.
I had a quick question.
Sure.
So U-bar, from that third step to the last step,
Mhm.
you substituted it with the 10 to the 1/2,
Correct. Mhm.
and that was the final answer from part A?
Well, to be fair, I guess the final answer for part A was what combination of goods would allow him to maximize his utility, right? So the answer to part A wouldn't be root 10, it would be 5 and 2, that he'd purchase 5 Twinkies and 2 sodas, right? Now, if the question had asked what level of utility does he derive from purchasing 5 Twinkies and 2 sodas, then we would have gone on to take the square root of 5 times 2 to get our answer. But the question merely asked for what combination of goods would you purchase to maximize his utility. I went back to part A to generate that level of utility, even though I wasn't asked for it, because I did need it for part B.
Okay, sounds good.
Good. Any other questions on that? I can go back and undo that if I need to. Okay, moving on to 4.2. It's a very similar problem that instead of talking about Twinkies and soda, we're talking about French wine and California wine. So we have a utility function that is equal to, for the sake of simplicity, I might use F for French wine and C for California wine, because then I get a lot of letters flying around here. So I'm going to say F to the 1/3, or F to the 2/3 times C to the 1/3. And again, F stands for French wine and C stands for California wine. Okay. This particular person's, or this particular connoisseur, she has $600 to spend. This is her income. The price of French wine is $40. Let's put a dollar sign again. And the price of Californian wine is $8. Once again, this is a Cobb-Douglas utility function. I have got some variable to a power times, it's important that this is a multiplication, times another variable to another power. So this is of the form that's Cobb-Douglas. Again, this is alpha. We call this alpha, and we call this beta. So bear in mind that 2/3 is our value of alpha, 1/3 is our value of beta. And with that in mind, everything should kind of flow pretty quickly as we go through these problems. Part A wants to know how much of each wine should this person purchase so as to maximize her utility. So F star will equal alpha times I over price of French wine times alpha plus beta. So we've got 2/3 times 600 over 40 times 1/2, sorry, 2/3 plus 1/3. It's going back to the old question where it's 1/2 plus 1/2, but this time it's 2/3 plus 1/3. Not that that matters too much, because after all this comes out to that, this guy cancels and becomes 1. But let's see, what do we get here? This ends up being, I think, 10 bottles of, let's even check my notes, but yeah, I think that's right. And that's some quick algebra there. 10, yeah, okay. And then we want to do the same thing for California wine. Again, the formula from the cheat sheet, just to show you one more time so you're not totally lost where I'm getting this. Just looking at the Cobb-Douglas, that's what this type of function is, and I'm looking at the utility maximizing choices of X and Y. But in this case, I'm not saying X and Y, I'm saying F and C, since those represents the different types of wine. So this time it's beta. I'm just going to drag this down. And instead of being alpha, it's beta. And instead of French wine, it's Californian wine. So let's make those small changes. California and beta. Okay. So we get 1/3 times 600 over Californian wine is $8 times 2/3 plus 1/3. And this ends up being 200 divided by 8, which is 25. Okay, so we purchase 10 bottles of French wine, 25 bottles of Californian wine. So 10 bottles of French wine, capitalized French, and 25 bottles of Californian wine, maximize her utility. It didn't ask for the actual level utility, did it? It just says how much of each should she purchase. I kind of want to, before we move on, I'll spend 30 seconds talking about why the values are the way they are. Notice that this 2/3 being a higher power than this 1/3 indicate that this person more heavily prefers French wine. However, she did not purchase as much French wine as she did Californian wine, given the price differential, right? The price of French wine costs $40 as opposed to $8. So this is the balancing act that's going on behind the scenes when you do a Lagrangian, is that this person prefers French wine, but she has to combat with the fact that its costs are 5 times that of Californian wine. So she doesn't purchase as much. However, she might purchase more than what you might otherwise would have thought, given the prices, right? Given that this is 40 and this is 8, you might think she might have much more heavily preferred Californian wine and just spent very little on French wine. But it is the case that she has a higher preference for French wine as given by the power on the value of f in the utility function. Okay, enough about that. That's part A. Moving on to part B. When she arrived at the wine store, our young enologist discovered, I guess an enologist is someone who studies wine, discovers that the price of French Bordeaux had fallen to $20 a bottle because of a decrease in the value of the euro. So if the price of California wine remains at 8, how much would she purchase to maximize her utility under these altered conditions? Cool. Well, that just means we got to make one small change. The price of French wine is now 20, and we recalculate. The nice thing is, this will not change because notice it did not depend on the price of French wine. Notice that nowhere in this formula for our utility maximizing Californian wine do we see the price of French wine. Do you see a PF anywhere in here? No, 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 no. There's no French wine price in that formula. So C star will not change. So for part B, we're still going to purchase 25 bottles of Californian wine. However, this number is no longer 40. It's now 20. And because that denominator is now 20 as opposed to 40, the amount of French wine this person will purchase is 20. That's part B. Part C, explain why this person is better off in part B than in part A. How would you put a monetary value on this utility increase? I think somebody asked this in the group me before, and I guess the best way to do this is to look at their expenditure functions. So we'll reference the expenditure function again. It's going to be slightly annoying. It's that alpha plus beta, but that's going to be 1. So 1 times U bar times price of French wine. Let's keep that at 40 to the power of 2/3 times 8 to the power of 1/3 divided by 2/3 to the 2/3 times 1/3 to the 1/3. And then this is all being raised to the 1 over alpha plus beta. But once again, alpha plus beta is 1. So I just want to figure out what this value is. And one last thing I'll do is use the utility that we would have gotten from, let's see. Yeah. So let's evaluate the two values of utility from the two cases. So in part A, how much utility did this person enjoy? So their utility would have been 25 to the, not 25, sorry. This person purchased 10 bottles of French wine, so it'd be 10 to the 2/3 times 25 to the 1/3. Let me get that as a decimal. So this is approximately equal to, snag a calculator here, 10 to the 2/3 times 25 to the 1/3. And this gives me 13.572. Now let's talk about how much utility this bundle gave this person. So the utility now would be 20 to the 2/3 because she was able to purchase 10 more bottles of French wine due to the price decrease. And let's figure out what the corresponding level of utility would be. It would be 20 to the 2/3 times 25 to the 1/3. This comes out to be 21.544. So here's what I'm going to do. I'm going to evaluate this expenditure function for the two different utilities we found from part A and part B. Now, technically, as Victoria said earlier, you weren't being asked to find the actual level of utility. You were only asked to find the combination. So in part A, your answer was 10 and 25, and in part B, your answer was 20 and 25. But because we want to put a monetary value on the utility increase for part C, it's probably best that we go find those utility values from part A and part B, even though we weren't asked to find them. So here's what we're going to do. We're going to take this 13.572. This will be our U bar here. Or go ahead and figure out what the level of expenditure will be, although we won't be too surprised when the answer comes out to be 600. You'll see why in a second. 13.572 times 40 to the 2/3 times 8 to the 1/3 divided by 2 to the 2/3. Oh, it's 2/3 to the 2/3. This is going to be a little annoying to type in. 2/3 to the 2/3 and divided by 1/3 to the 1/3. Using a calculator. This comes out to be 599.996 G. It looks very awfully close to 600, and that's probably because I used some rounded value. I used a rounded value here, so we'll just say it comes out to be 600 when I plug in 13.572. This makes sense though, because in this first situation, how much income did she have? She had an income of $600, so it only makes sense that when we use that $600 at the get the initial prices, we were able to generate 13.572 units of utility. Then going back to an income or using the expenditure function, we should only expect to go back to that $600. However, this time around, the second time around, we're now going to use this second utility value. We're now going to use this 21.544 and plug that in here and figure out how much money she would have to have spent in order to get that, keeping at the old prices. So I know that part B said the price had gone down to $20. But we want to measure the value of the utility increase relative to the old prices. So we're going to go back and keep that 40 here. We don't want to put 20 here. And let's see what happens. 21.544 times 40 to the 2/3 times 8 to the 1/3 divided by 2/3 to the 2/3, and that divided by 1/3 to the 1/3. So this comes out to be 952.425. So let's say this. This is the amount that she would have had to spend, weird sentence construction, she would have had to spend at the old prices of 40 and 8 to be as happy as she was when the price dropped. Let's say the French wine price dropped to $20. So she would have had to have 352-ish more dollars. Well, I'll put a dollar sign in there. She would have had to have 352 more dollars in order to be as happy as she was in the second scenario due to the price decrease. And I think that's your answer. That should be your answer to C. At least this is how I would measure it. Any questions on that? Okay. We are now going to move on to 4.5. Mr. A derives his demand for utility to martinis according to some pretty simple formula. He basically gets 1 unit of utility for every martini he drinks. Mr. A is particular about his martinis, however. He only enjoys them made in the exact proportion of 2 parts gin to 1 part vermouth. Hence, we can rewrite Mr. A's utility function as the following. U equals min of G divided by 2, comma V. I want to point out right off the bat that this is one of the known utility functions that I have on my cheat sheet. Which utility function has a min? Not this, not this, not this. It's this guy. This guy is your perfect complements utility function. So with that in mind, we're going to be using a lot of this row for this question. I might use just about all of it, but let's jump back to the whiteboard. First question wants to know, graph Mr. A's indifference curve in terms of G and V for various levels of utility. So what that's going to look like is, let's look at a set of axes. We might have talked about this in an earlier homework, like homework 1. This particular shape came up. We'll put G on this axis and we'll put V on this axis. And pick a level of utility that's really simple to work with, like say U equals 1. So what values of G and V would cause both of these to equal 1? So if I wanted G over 2 to equal 1, G would be 2. Similarly, if I wanted this to be 1, V would be 1. It's pretty simple. So let's go find that coordinate. G is 2. Now let's do it right here. 1, 2, and we'll do 1. So this coordinate marks what is going to be a kink in the indifference curve. These are what the utility curves look like, or the indifference curves look like for perfect complement utility. Let's do another utility value. So we just did U equals 1. Let us instead try U equals 2. So if U equals 2, what value of G would need to be taken on? So I get a 2 here and I would get a 2 here. Well, b would be 2 automatically, but that would mean over here, g would be 4. So that would be a point that is 3, 4, and this will be 2. So this point would be another indifference curve. This would probably be enough as far as I'm concerned. As long as you draw at least 2 indifference curves, you're good. But if you wanted to draw a third, it looks like it'd be something like this. And if you wanted to even label them with certain values of utility, u equals 1, u equals 2, u equals 3. So this is your answer to part A. There is some additional comment that they say, something like, show that regardless of the prices of the 2 ingredients, Mr. A will never alter the way he mixes martinis. I don't even know what that is asking. It says that Mr. A will never alter the way he mixes martinis, but that's inherent to the formula for you. So I don't know if you're supposed to say something like, I have no idea. The way Mr. A mixes martinis is in the proportion of 2 to 1. 2 to 1, was it gin and vermouth? Yeah. 2 to 1 gin to vermouth. And prices won't change that because I don't know. I don't even know what they want you to know here. Like, this is his utility function. The prices aren't involved. I guess I'll say prices won't change the structure of his utility function, I guess. Actually, you know what I have? I can toggle back to the very back of the book because this is a odd numbered question. Cool. It doesn't say anything. Just they even skip. They cleverly omit part A, but they have part B, part C, part D. So whatever. I mean, leave. I don't know what. Honestly, I don't think your professor cares if you like write some exposition about why his preferences won't change. At the very least, you should have this. This is going to be the most important part about part A for this question. All right, moving on to part B. Part B wants to know, calculate the demand functions for G and V. Those are straight out of my cheat sheet. So let's go find them. Perfect complements, demand functions. Here they are, right here. Bear in mind that you need this value of B and A, which come from the coefficients of X and Y inside the utility function. So in our case, I believe it's 1/2 G. So A is going to be 1/2 and B is going to be 1. But I'm going to be using these demand functions right now. So we have G star equals, it's B times I over B price of G plus A price of V. In our case, like I said, A is 1/2 and B is 1 because the coefficient of V is 1. Okay, so we have 1/2 I. So no, sorry, just 1 I. 1 times I over 1 times price of gin plus 1/2 times price of vermouth. You could do some simplification using algebra to get 2I over 2PG plus PV. Let me see if that's consistent with the answer key as well. 4.5. Yeah, I over PG plus PV over 2, which is what I have here, but you can simplify it to become this. All right, let's go ahead and find V star. Well, from my cheat sheet, that would be A times I over, this guy stays the same, so I'm just going to keep it, equals 1/2 times I over 1 times PG plus 1/2 times PV. After some simplification, doing some little bit of arithmetic, you get I over 2PG plus PV. Let me see if that answer is also consistent. 2PG plus PV. Yep. And by the way, don't ask me. You shouldn't be asking me at this point, hey, Andy, how did you go from this writing of it to this? You should know the little bit of pieces of algebra and arithmetic to rewrite some complex fraction by getting a common denominator down here, flipping the bottom fraction to the top and canceling the 1/2. But I hope you can do that. That should be pretty straightforward. Although even if you don't, honestly, even if you are unable to get to here, I don't think your professor cares too much. You can leave your answer just like this. Okay, part C wants to know indirect utility function. What's the indirect utility function? Where could I ever find the indirect utility function? How could I ever? First off, it sounds a little weird, right? I've heard of a utility function before. What's an indirect utility function? Oh, you know what? Doesn't matter because it's on my cheat sheet. There it is. Indirect utility is the third column. We're again talking about perfect complements. So your answer is ABI over BPX plus A times PY. So cool. I have all that. That would be 1/2 times 1 times I over B, which is 1 PX, not X, but G, plus, let's use lowercase g, plus 1/2 A times PV. So we get, all told, we get I over 2 PG plus PV after simplification. So that's your answer to C. Any questions on A, B, or C so far? Okay. And then we want the, I'm sure it wants some sort of expenditure function. Calculate Mr. A's expenditure function. Cool, great. I have that in my cheat sheet. Expenditure function for perfect complements is U bar times PX, or I guess PG, over A plus PV over B. In this case, we don't know what U bar is, we leave it as U bar. We don't know what PG is, we leave it as PG. However, we do know the value of A is 1/2. We don't know the value of PV, we leave it as PV. But we do know the value of B. So after some small simplification, you can call this U bar times 2PG plus PV. And that would be your expenditure function. Any questions on that? All right, that's 4.5. Let's keep trucking along to 4.8, I believe is the next one. 4.8 kind of continues off of what we just did in a similar fashion. It says two of the simplest utility functions are fixed proportions and perfect substitutes. So fixed proportions is the kind we just did. Let's start with fixed proportions, aka perfect complements. And then we're going to do it over here as well. We'll do perfect substitutes. So let me type. There we go. Perfect substitutes. Okay. Now, my name's just hanging out there. Oh well, it's a glitch. Okay. Fixed proportions, aka perfect complements. What do they want from us the first time? They want us to compute. For each of these utility functions, compute the following: demand functions. So demand, indirect utility, I hesitate to even do this problem because you can literally just rattle off what you need from my cheat sheet, but it's fine. And then expenditure functions. Let's start with perfect complements. Let's kind of like make this like a small table. Okay. Demand functions for fixed proportions is, and by the way, I'm literally copying this off my cheat sheet. 1 times I over 1 times price of X plus price of Y, or 1 times price of Y, which would simplify to I over price X plus price Y. And Y star would be very similar because this changes from a B to an A now, but A was 1, so it's still 1 times I over, same thing, which is I over price X plus price Y. So these are your demand functions for both X and Y. I want to make sure that's what I have here. Okay, cool. And then your indirect utility, we'll call it, I call it V, yeah, I'll call it V, is A times B times I, which is still 1 times I over 1 times price X plus 1 times price Y. Okay, cool. It ends up being, once again, I over price X plus price Y. Okay, how about expenditure? Once again, we have U bar times price X, which is, leave this price X over 1 plus price y over 1. That's it. That's all there is to it. For perfect complements, or sorry, for perfect substitutes, things are a little trickier. Perfect substitutes, you have a couple cases. So if things are perfect substitutes, that means you're going to, let's just say what goes on here. You either buy all of one or all of another. That is to say, if I get a better deal from the first good, then I'll buy all of that. If I get a better deal from the second good, I'll buy all of that. And I don't really want any balance. It's not like I need any balance. They're perfect substitutes. It's not like I'm saying, oh, you know what? I need some of the other thing. No, I don't need any of the other thing if I can buy the other thing or the first thing more cheaply. So the way this works is X star and Y star are kind of piecewise functions. I've done it in a way that is a little weird on the cheat sheet, but it was the best way I could try to combine it into one small cell. So I'm going to write it in this way. X star is either I over px if the price of x is less than the price of y, and it's 0 if the price of x is greater than the price of y. And then y star is kind of the other way around. It's 0 if the price of x is less than the price of y. If it's cheaper to buy x, I'm just going to buy x. But if it's cheaper to buy y, then I'm going to spend all my money on buying y. And then I guess there's one small caveat here is that if the prices are equal, then I'll spend my money, then I'll say anywhere on the budget constraint makes me happy, makes me equally happy. Then any point, well, that makes me as happy as any other point. Basically, I'm indifferent, right? If the prices are equal, well, who cares? I'll buy just as much X as Y, and I can use them interchangeably because they're the same, they're identical. We're basically saying that if they're perfect substitutes, the goods X and Y are identical. And if their prices are identical, then they might as well just be the same good. So it doesn't matter how I divvy up my money. But if they are the same good, but they have different prices, then I'm going to spend more money on the thing that costs less. Spend all my money on the thing that costs less. Okay. That said, we can mosey on over to indirect utility, which is, yet again, on my cheat sheet, we're looking at the third row for perfect substitutes, and that's just V equals maximum of AI. Well, A here is 1, so just say I over PX, comma, I over PY. And how about expenditure? Expenditure, by the way, you could say this in another way if you rather say it in a different way that doesn't involve the max function. You could say V equals I over PX if price of X is less than price of Y, or it's I over PY if price of X is greater than price of Y. By the way, let me know if this is going off the page. I know that some people can't see this sometimes, but should have enough room where we can see everything. Okay, and then expenditure function. Again, just looking at the cheat sheet. E equals min of U bar times price X, comma, U bar times price Y. They technically have a divided by A and divided by B, but those are 1 and 1, so they don't change anything. Okay, that's 4.8. Oh, that's part A, I guess. Part B wants you to write a little essay or a small sentence. Discuss the particular forms of these functions you calculated. Why do they take specific forms they do? I have no idea what they're asking there. That's so open-ended that I don't know what they're trying to drive at. I mean, if the question is why, I mean, like we can talk slightly about, I've kind of said why X star and Y star take the form they do for perfect substitutes. Because if the price of X is cheaper than, if it's smaller than Y, then I'm going to spend all my money on X. But on the other hand, if the price of X is higher than the price of Y, I'm going to spend all my money on Y. I don't know if that's like if you're supposed to put in words why the demand functions are the way they are, but that's one way of doing it. Yeah, I don't know what more that you're being told to say here, or what you're expected to say here. So that's 4.8. Excuse me. Okay. Next is 4.11, I believe. We have the CES utility. So 4.11. CES utility is U equals X to the delta over delta plus Y to the delta over delta. And this is if delta is not equal to 0. But then U equals ln of, they don't say this in the question, but it's kind of annoying that they don't. I guess they say that if in the instance where delta is 0, you're supposed to revert over to this version of this function. I guess. I don't know. We'll see. Show that the first order conditions for constrained utility maximum with this function require goods in the proportion, blah, blah, blah. One thing we can do, I guess we can use the MRS. So this will require a little bit of Lagrangian, if unfortunately. Well, let's see. Let's see how much we can get away with. There's two. Let's do, yeah. Rather than use the Lagrangian method, I will use the MRS equals price ratio method as a way to find the optimum values of X and Y. Okay, so this method is a shortcut, kind of shortcuts the Lagrangian. So it's called the MRS equals price ratio method. And the MRS equals price ratio method, when I say price ratio, I mean price of X to price of Y. So that means price X over price Y. Just bear that in mind. MRS is something you computed, well, a few weeks ago now. It's been a few weeks since you've probably ever computed an MRS. But that is the marginal utility of the good X divided by the marginal utility of the good Y. And remember, marginal utilities, the word marginal usually means to take a derivative. Marginal utilities are the derivative of the utility function with respect to the variable you're asked to find the marginal utility for. So in our case, the MRS is partial derivative of this guy with respect to X. That would be X to the delta minus 1. And then this term would go away because its derivative is being taken with respect to Y, with respect to X, and so it's treated as a constant. But now we're going to flip the script. Now we're going to go through and take the partial derivative with respect to Y. Because of that, this term as a constant will go away, and the partial derivative of this term with respect to Y is Y to the delta minus 1. Okay, and we're going to set this equal to, like I said, to the price ratio, Px over Py. Let's start solving here. Actually, you know what we'll do is there's not too much solving to be done. Notice that X and Y are being raised to the same power, so you can write it like this. If X and Y are being raised to the same power, then you can put them in the same parentheses as long as they're being multiplied. So what do I mean by that? If you have X cubed times Y cubed, you can write that as XY cubed. Do not make this mistake. I can't tell you how many times I've seen people make this mistake, although realistically, it's usually OU students who are making this mistake. Trust me. I've tutored them for a while as well. You cannot do this. This is a big no-no. Cannot do that. But as long as they're being multiplied or divided, and as in the case over here, you can put them in the same parentheses. So that's what I've done here. X is being raised to the delta minus 1. Y is being raised to the delta minus 1. So I'm going to put them in the same parentheses because the X and Y's are being divided, and say X divided by Y to the delta minus 1. Now, my job is to get my hands on just the ratio X divided by Y. So what would I do to both sides of this equation so as to get rid of this delta minus 1? Let me do something else. Let me kind of show you an example. If I said A squared equals Z, what would I do to both sides to get my hands on A? I would just take the square root, right? I would say, actually, A equals Z to the 1/2. We'll ignore the plus or minus that I was technically supposed to have, but forget that for now. Z to the 1/2 is what we'd say there. In a similar fashion, if I had B to the 3rd equals W, I would get my hands on B by raising both sides of the 1/3, and I'd say B equals W to the 1/3. Same thing holds here, that the power on X divided by Y is delta minus 1. So in order to get my hands on X divided by Y, I would raise both sides to the power of 1 over delta minus 1. Like this. That simple. And that's all we need to do for part A. So this is the work that I've shown for part A to get that answer. Okay. Part B, show that the result in part A implies that individuals will allocate their funds equally between X and Y. Say delta equals 0. So we're going to say to part B, let's plug in 0 for delta from into our answer from part A. Let's see what we get. So we get X divided by Y equals price X over price Y to the power of 1 divided by 0 minus 1, which is another way of saying X over Y equals price Y over price X. This power becomes -1. I hope you guys realize that 0 minus 1 is -1, 1 divided by -1 is -1, and a negative power means you flip the fraction. So we have X over Y equals price Y over price X. And here's what we're going to do. The last thing we're going to do is now cross multiply. So we get X times price of X equals Y times price of Y, and we're done. Why are we done? What does part B ask us to do? Part B asks us to show that we will allocate our funds equally between X and Y. So this amount here is the amount of money I allocated to buying X. In a similar fashion, this amount here is the amount of money I allocated to buying Y. But I've shown what I need to show because the question says, show that you end up spending as much money on X as you do on Y. So that part is done just by doing a little bit of algebra from part B. I plugged in 0 for delta. I got this new fraction here. Instead of px over py, it becomes py over px because the power is -1. And then I just cross multiplied. And once I did that, I get x times px equals y times py. Guess what? That's saying the amount of money I spend on X is the same as the amount of money that I spend on Y. And that's all part B wants us to do. Okay, part C. Part C says, how does the ratio px times x divided by py times y depend on the value of delta? Dude, I have no idea. One thing that I think might be useful, this is the one I'm kind of stumped on so far. I'll probably get back to you on this one, but for part C, I think what this is asking is, let's make some room here. I think this is, I think page 166 for the textbook helps. I reference this in my notes. Page 166, if you dive on over to that, hold on, give me a sec to go page 166. Oh, by the way, I mean 166 PDF number, not, so page 166 PDF number, but that also corresponds to page 142 in the book page. It says that the share of money, let's see. Okay, yeah, here's why. All right. So X times PX, as we'll find out later, divided by I, is the share of money that we spend on X. So this is the share of money, share of income spent on X. They tell us on page 166 of the PDF or page 142 of the book, they tell us that SX equals this disgusting thing, 1 over 1 plus, oh, I'm going to need more room than this, 1 over 1 plus py over px raised to the delta over delta minus 1. Cool, great. This doesn't seem useful at all. And similarly, the share of y would be 1 over 1 plus price of x over price of y raised to the delta over delta minus 1. Okay, now why is this useful? Because they say, or part C says, talk about x times price of x over y times price of y. Oops, that's price of y, and how they're related based on delta. But guess what? X times price of x and y times price of y are related in the share values. That is to say, if I take Sx and divide by Sy. Not these formulas, but this definition. I get x times px over I divided by y times py over I, which ends up being x times px over y times py, the very thing we're being asked about over here on the left. So here's what I'm doing, is that I'm going to move these things around. This guy is the same thing as this guy, is the same thing as this guy, equals, 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 is the same thing as these two things on top of each other. So this guy, well, let's move this here. Let's move this first here. And let's move this guy here. After some algebra, I guess this becomes 1 plus py over px to the delta over delta minus 1 over 1 plus px over py to the delta over delta minus 1. And this is the closest thing that I have coming to an answer. Doesn't make much sense to me, to say nothing of the fact that I don't even know how you would begin to explain these answers, this answer intuitively, which is what it told me to do. Although maybe it wants us to do it for this particular case. Maybe that was the question. How does the ratio of px times x over py times y depend on the value of delta? Oh, because it depends on delta, so it's not this particular case. I don't know. I have no clue. So I'm gonna do some thinking on part C and get back to you guys on that. But for now, that's all I've got. And then we have part D to do now. So this is 411 part D. Derive the indirect utility and expenditure functions for this case and check your results by describing properties of the functions you calculated. So annoyingly, this is not on my cheat sheet. I have CES utility. And like I said, these are too messy to solve by hand. Now, sorry, I should say they're too messy in this case. But remember, we're dealing with the case of ln of x plus ln of y because they told us delta was 0. So this actually is doable, and we'll just do it the long way using a Lagrangian. So let's jump back to the whiteboard, and we'll say u equals ln of x plus ln of y, and we will derive the utility maximizing conditions or values of x and y using the Lagrangian, or I might even use the price ratio method, or MRS equals price ratio method. Yeah, in fact, I'll just do that. So let's do again, using the MRS equals price ratio method. We'll end up with 1 over x divided by 1 over y equals price of x over price of y. This becomes y over x equals price x over price y, something we saw earlier. Cross multiplying gives us x times price of x equals y times price of y. I can now that I have this relationship, I can take this guy and substitute it in for y times price of y. So I get x times price of x plus x times price of x equals I. And this gives me 2 times x times price of x equals I, which means when I solve for x, I get x equals I over 2 price of x. In a very similar fashion, y will equal I over twice price of y. Okay, now that I have x star and y star, I can go ahead and get what the indirect utility function is by taking ln of x and ln of y, but replace them by the values we just got for x and y a moment ago. So I'm going to put this in here. I'm going to take this, put it in here. And you could leave it like that, although it's going to be easier to begin to solve for I when we do a few things with algebra. So one thing you might learn back in calculus or some pre-calculus class, when you add 2 logs of the same base, you multiply their arguments. So this will become ln of I squared over 2 times price x times price y. So it ends up with 4 times price x times price y. And so this is your indirect utility function. Now, I want you to find, so this is, they wanted you to find indirect utility function and expenditure function. So this is the indirect utility. How do you get expenditure function? That's pretty easy. Just solve the indirect utility function for I. This is how you always do it, or at least, yeah. I mean, I don't want to say always, but for the most part, yeah. Okay, so I want the expenditure function. That means taking this indirect utility, V equals ln of I squared over 4px plus, or 4px times py, and solving for I. What would I do to both sides to cancel the ln? I would do an e to both sides. So I have e to the v equals I squared over 4px py. And then I'm going to multiply both sides by 4 times px py and take the square root. So I'm going to end up with 2 square root, let's just say this. I'm going to end up with I equals square root 2 times the square root of px times py times e to the v. Or you could say u bar, because those are the variables we use. So let's say e to the v, but then I'm going to say a few things that we can do to simplify this. One is we don't tend to call expenditure functions I, we tend to call them e. So that's one thing. Furthermore, I can say 2 square root of px times py, and then I could say e to the v over 2. Will that scare you guys? Yeah, probably. Some of you guys aren't the best mathematicians. So I'm going to keep that e to the v inside the parentheses. However, I'm going to call it e to the u bar. And again, I'm calling it e to the u bar, or I'm replacing v by u bar to be consistent with what my cheat sheet says, that I'm using u bar as the fixed level of utility inside the expenditure function rather than v. Okay, so that's all that we did going from here to here, was we just swapped I with e. Let's just point that out. I swapped I with e, and I changed v to u bar. That's all I really did. Okay, that is 4.11. Are there any questions on 4.11? Okay, I'm going to keep it going. What is next? I think hold on. I've got I think, is that all of? Let me check real quick.
Next is 414.
Thank you.
Parts A, B, and C only.
414. Parts A, B, and C. Okay. Gotta find that in the book. Sorry, give me a sec. Oh, is this the altruism question?
Yeah.
I love this question, and I can almost see it being like a test question. This is totally a test question that he would do. So let's talk about this one. Where is my whiteboard? There it is. This is 414, the altruism question. Michelle, who is relatively high income, has altruistic feelings towards Sophia, who lives in such poverty that she essentially has no income. Suppose Michelle's preferences are represented by the utility function C1 to the 1 minus a times C2 to the a. What kind of utility function is this? Well, it's kind of like a Cobb-Douglas, because actually for the most part, we'll just say it is. Yeah, it is a Cobb-Douglas, because it is C1 to some power times C2 to another power. Yeah, appearing as goods in a standard Cobb-Douglas utility function. Okay. Assume that Michelle can spend her income on either her own consumption or Sophia's consumption through charitable donations, and that $1 buys a unit of consumption for either. Thus, the prices of consumption are P1 equals P2 equals 1. So we've made things simple, so that the price of good 1 is $1, and the price of good 2 is also $1. That makes sense, right? Me spending $1 on myself, in terms of the prices don't change based on who buys it. Whether I'm buying it, if I'm buying a gallon of milk for myself, it doesn't change if I were to say, if I were to buy that same gallon of milk for somebody else. So the prices are the same, and they're going to be reflected in the fact that they're both a single dollar. Okay. Argue that the exponent a can be taken as a measure of degree of Michelle's altruism by providing an interpretation of extreme values a equals 0 and a equals 1. I love this question, the way this is set up, because what it's saying is, let's look at some extreme values of a. Let's suppose a were 0 versus suppose a were 1. What does this mean in terms of the utility function we get? If a is 0, the utility function becomes C1 to the power of 1, and then times C2 to the power of 0, which is just C1. And vice versa. If A is 1, then the utility function becomes C1 to the 1 minus 1 is 0 times C2 to the 1, which becomes C2. If my utility function equals C1, this means money spent only on me makes me happier. Or only on, I guess this is not me, but the person who has the money here, Michelle. Money spent, Michelle only, this is Michelle's utility curve, so let's bear that in mind as well. This is Michelle's preferences. Michelle only derives happiness when she spends money on herself. So this is like perfect selfishness. Okay. Conversely, this is U equals C2. Can anyone provide me with an interpretation of this utility function?
She only derives happiness when she spends money on Sophia.
Yep. The only derives happiness when she spends money on Sophia, the person who is so poor as to have no income at all. So this is, I don't think this is what's considered perfect altruism, because I think in the next part it says that perfect altruism is to treat everyone as yourself. So I think that says, yes, what value would make her a perfect altruist regarding others the same as oneself? So this would be perfect. I don't know. I don't even know what this would be, because, so by the way, for those who don't know, I probably should have said this at the beginning. What is altruism? Let's look at a dictionary definition just to get it straight. But that is just like feelings of charitability. Let's see. The belief in or practice of disinterested and selfless concern for the well-being of others. So altruism. The belief in or practice, let's just say the belief in selfless concern for the well-being of others. So that's basically, I think of it as charitability. Altruism is synonymous with charitability, is the way we think about it. However, this book says, it seems to suggest that perfect altruism, a perfect altruist is where you see yourself as equal to other people. So I don't know if this is perfect altruism. I guess this would be perfect selflessness. That is basically saying Michelle isn't even a concern, isn't concerned about herself. Basically would give all her money to Sophia. So it's perfect selflessness. So these are the extremes. As you can probably guess, what would be a happy medium? What value of A would represent a happy medium wherein she sees herself as equal to Sophia? I spoiled it. I wrote 1/2. I'm an idiot. I was talking and I started writing 1/2. Whoops. So as you can probably guess, if A equals 0 represents perfect selfishness and A equals 1 represents perfect selflessness, then A equals 1/2 represents the perfect altruist, where you have C1 to the 1/2 times C2 to the 1/2. And that represents where Michelle sees Sophia as her equal. Okay. Toggling back over to the book. Solve for Michelle's optimal choices and demonstrate how they change with A. Okay. The nice thing is this is still a Cobb-Douglas. So optimal choices, C1 star equals. We're going back to using this guy. So these are all gone now. We don't actually have to use these anymore. C1 star equals 1 minus alpha. So not alpha. One second. Just want to point out, again, this is Cobb-Douglas. So use cheat sheet. Here, alpha equals 1 minus A, and beta equals A. So with that in mind, C star would be 1 minus A times her income. No, wait, is it? Yeah, it's alpha first. Okay, so alpha times I over price of C1, but we know that to be $1, times alpha plus beta. So 1 minus alpha plus alpha. Nope, sorry, 1 minus A. I keep screwing this up. It's not alpha, it's A. This is A. This is A. Yeah, I know. Lowercase a and alpha are pretty much the same thing. And then plus beta, which is A. So this boils down to just 1 minus A times I. And then C2 star will be very similar. It's beta, which is A, times I over the price of good 2, which is again $1. So 1 times alpha plus beta. Alpha is 1 minus A, beta is A is canceled, and I have A times I. So these are her optimal choices for C1 and C2. By the way, these would be consistent with what we said before, that if A were 0 and she were a perfectly selfish, what would she do with her money? All of her money would go to, let's see, 1 minus 0 times I would be I here, and this would be 0 times I, which would be 0, which is saying that she would take all of her money and spend it on her own consumption, and she would take none of her money, none of her dollars, and spend it to help Sophia. That would be consistent with what we said earlier for part A of perfect selfishness. Okay, not that we had to show that or anything like that, but I just thought it's worth noting that, again, it's consistent with what things we derived before. Okay, part B. So solve, demonstrate how they change with A. I don't know what they want you to say. We found C1 star, we found C2 star. That's part B. Move on. Part C. I don't know what you mean is demonstrate how they change with A. You could say, actually, no, I think you could say, like, do you want to say the derivative of C1 star with respect to A? And say that's negative I. So what does that even mean? That means that as A increases, C1 star decreases. I don't even think, no, doesn't even seem useful. We'll ignore that. Back to C, though. Solve for Michelle's optimal choices under a income tax at rate T. How do her choices change if there's a charitable deduction? So income spent on charitable deductions is not taxed. Does the charitable deduction have a bigger incentive effect on more or less altruistic people? This is an interesting question. I think what this is saying is income spent on charitable deductions is not taxed. So that means I'm trying to figure out how this actually represents itself in either the utility function or the let me think for a second. Michelle's choices on income tax rate T. How do our choices change for charitable deduction? Income spent on charitable deduction is not taxed. So that might be represented in the budget constraint. So our current budget constraint is 1 times C1 plus 1 times C2 equals her income. So I'm going to draw that out. C1 plus C2 equals I. That's pretty consistent with what we said before. She can spend money on herself, she can spend money on Sophia, and she can do so in such a way that it never exceeds her income. She could spend 75% of her money on herself and 25% on Sophia. She could spend whatever, different allocations, different ways.
Quick question.
Yeah.
That wasn't given, but we did assume it, right? Given the information.
For sure. And this is the budget constraint is usually, I will say this, the budget constraint is almost always assumed to be, X times price of X plus Y times price of Y equals income. And that's kind of present in every type of problem that you're doing when you do utility maximization or consumer choice theory. Things are getting a little hazier here because there is a charitable deduction or there's a tax. So I've got to figure out how this tax works. That is, I guess this would be minus T times I. So does this make sense? I'm saying that if you have income I, then your true income, that's, again, I should say true in air quotes here, true income after, let's just say, we'll call it after tax. Your after tax income is I times 1 minus T. Let's see if that makes sense. Let's say you have $100. And let's say the tax rate is 30%. Then what is your after-tax income? Well, if you take 30% of your income and you tax that $100 by 30%, you're left with $70. Does the formula that I gave, it's 70, the formula that I gave here consistent with that? Well, that would be 100 times 1 minus 0.3, which would indeed be $70. So I think what's happening here is that there is a tax on the income. However, this actually can't be right either, because it's really only the money you spend on yourself that's taxed, not money that you spend here. So I really shouldn't put the minus TI here. It should be something like, it's probably like this. Because, is that how it should be thought of? I'm not actually sure how to approach this. Because you're not being taxed on money you spend on Sophia, but you are being taxed on money spent on yourself. Income spent on charitable deductions is not taxed. Or you know what I should do? Rather than do this, rather than say, let's take the tax away from, we'll do this. We'll say 1 plus t. This is how it should be set up. Yeah, I'm almost positive on that now. Here's what this is saying. This is saying that the price of spending money on yourself is $1 plus tax. But let's move this around a little bit. But the price of spending money on your friend on charity is still just $1. Right? We can see that the coefficient of C2 is 1, and so the price of charity is still $1. Or for every dollar you give away, you're not being taxed on it. However, price of spending money on yourself is not just $1, it's $1 plus whatever you're being taxed for. So this is the budget constraint. So kind of go back to what you asked, Victoria. Your standard budget constraint is always, always, always xpx plus ypy equals I. But in some weird, there will be some instances where it will be made stranger by throwing in a tax or saying that income has been supplemented or reduced in some way. And this is the way that there's a tax involved. So with that in mind, we're just going to recalculate our values of C1 star and C2 star. Remember, C1 star was 1 minus A times I over the price of C1. Well, the price of C1 is no longer 1 anymore. The price of C1 is 1 plus the tax, so 1 plus T, and then times 1 minus A plus A. That's still going to be the same here. That's going to come out to be 1. So we get 1 minus A times I over 1 plus T. And then C2 star equals, it actually stays the same because not the price of 2 didn't change. So this just comes down. This just comes down and stays the same. And what is the effect here? You can kind of see what we went from this here. Let's kind of put a cloud around it. We went from this guy as money we spent on ourselves to this guy as money we spent on ourselves. What happened? The only meaningful difference between these two formulas is this 1 plus T sitting in the denominator. But what is that going to do to the value of C1 star? I mean, T is presumably some positive, some non-zero tax. So T could be like a 30% tax, or T could be a 20% tax or something like that. And so with that in mind, what would the value of C1 star be? Or as a result of having this 1 plus T term down on the bottom? It would just be much less. It would be, it's decreased. We're dividing by, we'll say that, dividing by this 1 plus T term causes us to spend less money on ourselves. I think this is all we need to do. Although it makes me wonder about some extreme cases, like what if your tax is 100%? What if there's a 100% income tax? Then the formula would still work. I don't see why this wouldn't. I mean, this would be fine. You would just divide by 2. Don't know why this wouldn't suddenly break, because if we had 100% tax, I guess it's just interpreted as income spent on a charitable deduction. I'll come back to that and I'll let you know if there's any update on that, but I feel like this is the best way to tackle this problem. So I'm done with that 4.14. That's all I want to say about that. Any questions on that? And again, if I think of anything else that might change this formula, I will let you guys know, but I think that's the best way to tackle that problem. Okay. Moving on to 5. Gotta scroll down in the book here, so give me a sec. What's the first one from 5? They want you to do probably 5.1, right?
Yep.
Okay. 5.1, Thirsty Ed drinks only pure spring water, but he can purchase it in 2 different size containers, 0.75 liter and 2 liter. Because the water itself is identical, he regards these 2 goods as perfect substitutes. So 5.1 is a perfect substitutes case. What do they want us to do for the first part? Assuming Ed's utility depends on the quantity of water consumed and the liters and the containers themselves have yield no utility, express this utility function in terms of quantities of 3/4 liter containers and 2 liter containers. So you can say U equals 0.75x plus 2y. What I want to say is that it's interesting what the book does. The book opts to say U equals x plus 3/8 y. Or they'll say U equals, wait, did I do that right? Wait, why does the book have that? Because if that's what the answer in the back of the book is, then it's just straight wrong. 5.1 says x plus 3/8 y. That's just wrong. Yeah, it's totally wrong, right? It has to be, because if I buy, let's say 6 of the small containers, how much utility would that bring me? Versus if I buy, and it'll say and 0 big containers, how much utility would that bring me? Versus if I buy 0 small containers, and let's see, is 6 the number I want? 6 times 0.75. Oh, you know what? That's not what I want. 8. And if I have 3 small containers, sorry, 0 small containers and 3 big containers, how much utility would that bring me? Bear in mind that these containers are perfect substitutes, except for the fact that they're different sizes, right? Small containers provide 0.75 liters of water, while the big containers provide 2 liters of water. So according to my utility function, how much would 8, let's do this in two ways. We'll kind of say my answer and the dumb book answer. Dumb book answer. Okay. We're going to type it. Dumb book answer. Let's take the numbers, we plug them into my utility function. Again, x is small, bear in mind, and y is large. This is what was stated in the problem. Is that right? Let's make sure I'm right about that before I go looking like an idiot.
Yeah, that's correct.
Okay. X is the small containers, y is the big containers. All right. Let's take 8 and 0 and plug them in for x and y respectively. That would give me U equals 0.75 times 8 plus 2 times 0, which would be 6. Okay, let's do the other point. What if I do 0 small containers and 3 big containers? So I'm going to do U equals 0.75 times 0 plus 2 times 3. That would also be 6. And this makes sense, because if I buy 8 small containers that give me 0.75 liters of water, I have 6 gallons of water. Same thing over here. If I buy 0 small containers, but I buy 2 large containers each, or sorry, if I buy 3 large containers, each containing 2 liters of water, I again get 6 units of utility, or 6 gallons of water, or 6 liters of water. Let's use the dumb book answer and see what happens. So I plug 8 and 0 in here. I get 8 plus 3/8 times 0. So let's just say 0. We get 8. Versus, now let's try the other point. If I plug in 3 for y and 0 for x, I get u equals 0 plus 3/8 times 3. And that would give me 9/8. Does that make any sense? No. I should have the same amount of utility in both of these scenarios, because 8 small containers, 8 small is the same as 3 large. And so the utilities should be the same. But that checks out over here, right? I got a level of utility of 6 for both scenarios, but I got 8 here and I got 9/8 here. So this is the dumb book answer. Don't look at the book for your answer here. Don't know why they provide solutions that are just wrong. So this is how you should set up your utility function. What more do they want from this, by the way? Okay, we did. That's all part A. Part A is, I didn't mean to go off like that. Really, honestly, all you needed for that was this, but I wanted to make sure anyone reading the back of the book didn't get confused by their answer, because their answer is just straight wrong. Now, you could argue that what they probably meant was like 3/8 x plus y. That would have been fine, because the small container is providing 3/8 the utility as the large container, so this would work as well. But I think mine's fine. I just figure, why not just scale utility by the sizes of the jugs? Okay.
So this might be a dumb question, but where did you get the original, like 8 small, 0 large, and 3?
Why did I pick those numbers?
Yeah.
I'm just looking at the ratio of these two. So what is 0.75 divided by 2? So that's fractions. 0.75 is 3/4 divided by 2. That's 3/8. So, like, it's kind of I kind of pulled them out of nowhere, but like, let's say that I picked 3 and 8 because they work really well given the ratios of the two sizes. So let's say like you have a 20 pound bag of candy. Let's say Twix. And then you have a 55 pound bag of Twix. In what ratios? How much this can I buy, and then how much of this would I buy to have the same amount? And it's just probably some sort of common, like, greatest common factor or something. Like I could probably do 5. No, what am I missing here? 11. Well, I could do x equals 11. That would give me 220, and then I could do y equals 4. The ratio of these two things is 4/11, right? So I know I can buy 11 20-pound bags of Twix, or I can buy 4 55-pound bags of Twix and have the same amount, right?
Yeah. Okay. That makes sense. Thank you.
All right. So part B wants us to state Ed's demand function. Okay, demand function. Cool. Demand function for x. Guess where you can find a demand function for perfect substitutes? My cheat sheet. It is I over price x, or 0, under certain circumstances. If, what does my cheat sheet say? I'm going to share screen on that. I lost it. Where did my cheat sheet go? Give me a sec, guys. There it is. X star equals I over PX if BPX is less than APY. In this case, B is 2 rather, and my value of A is 0.75 according to my according to my function that I created. So again, I'm just using my cheat sheet. If 2PX is less than 0.75 PY. But it's 0 if the other way around. If 2 times the price of X is bigger than 0.75 times the price of Y. Do they want just for X, or do they want it also for Y? Let's see. Oh, just for X. And they want it in terms of PX and PY. Yeah, we've done it. So this is what they want. Let's see what the answer key said. I'm just curious. It says I over PX if PX less than or equal to, sure, I like what that said. They said less or equal to. That's fine. You don't have to have it though. But it just, the or equals to case deals with the situation where what if the price ratios are the same as the marginal utilities? And so what will we do? That was where I said you would be equally happy purchasing any point on the budget constraint as any other. So they're just taking care of that by putting an or equals to here. Okay. Let's see. I over PX and then 0 if it's the other way around. They said, or the book says I over PX if PX less than, go to 3/8. So they say I over PX if PX less than or equal to 3/8 Y, or price Y. Hopefully you guys see that these are the same thing. This inequality is the same as this inequality. What have they done to both sides of this inequality to get this inequality? A very obvious thing have they done to go from the left to this inequality on the left to this inequality on the right?
Just divided by 2?
Yeah, so this inequality is what I'm using just from my own cheat sheet. They took my cheat sheet and they used it and then they said, you know what, I'm going to simplify it so that I don't have a constant on this side and just divide both sides by 2. That doesn't make this right or mine wrong, or it doesn't make mine right or theirs wrong. These are equivalent statements. So just bear in mind that theirs looks a little different than mine. Okay, we don't need to find a Y star. You were not asked to find that, so we're not going to. Part C wants us to do what? Graph the demand curve for X holding I and PY constant. Okay, I guess we could do that. Graph the demand curve for X holding I and PY constant. So what are this is going to be price of X. And this will be X. That usually, so in economics, we tend to put price on the x-axis, or on the y-axis rather, and put X here. So I guess I'll do that. What do they say in the key? I don't even think they draw it, do they? Of course they don't. Okay. We're holding I and PX constant, so I guess you would do something like this. It's probably something like this, but then there's a point at which, let's do this in blue. I think this is what the demand curve is supposed to look like. The question is, how did I get this nonsense? So first things first is, here's my demand curve, I over PX. You're holding I constant. PX can move though. What this means is, here's what I'll do. Let's pull up a tab. Wolfram alpha. Plot y equals 1 over x. What I want to show you is this graph real quick. Y equals 1 over x. What does this look like? We're going to ignore the lower left corner because we're in economics, and so there's no such thing as a negative value for x or y. So we get this kind of curve shape. And sure enough, that is exactly what I have here. But then the question is, why this weird L shape? All I know is this happens because, oh, I know why this happens. At some point, the price of X becomes too high. And if the price is too high, what happens to your demand curve? How much of X do you purchase? Well, if the price of X gets too large, suddenly you'll go and purchase how much of it? I'll just move this. Here's what I should do. I don't need this. What I really want is kind of like this. Yeah. So this is the demand curve. The demand curve looks, so here, that's what I'll do. I will highlight this guy, and this guy is this piece. But then we'll do in green. This guy is this piece. It's a piecewise function. There are two pieces involved here. So in certain instances, it's 0. That is to say, you purchase how many units of X? How many units of X would you purchase if the price is too high? You'll purchase how many units of X? You'll purchase 0, which is what this is saying. Otherwise, if the price is right, you'll opt to purchase I over PX, And that's a curve that looks like what I showed you on Wolfram Alpha. So this is what your demand curve looks like. So really we're looking demand curve, but it's piecewise function. So let me erase a few things. Got too many pieces here. Long story short, this guy goes to this guy, and this guy goes to this guy. If the price is too high, like I kind of put it in words what's going on here. If the price is too high, price of X, we'll say, we'll buy 0 units of X. But if the price is low enough, we'll buy according to the curve I divided by PX. And what does PX look like? Looks like this guy. But the price is too high, we buy nothing of X. Okay, hopefully that clears that up. D. How do changes in I and PY shift the demand curve for X? So increasing I, let's show you, I want to show you, see if I can show you on the plot. Well, let's just graph it. Here's 1 over X. Here's 2 over X. Here's 3 over X. Notice that when this numerator is increasing from 1 to 2, then from 2 to 3, and so on, it's causing this curve to kind of move up. But the price ratio, so it kind of like moves this out, I guess. Yeah. That's what would happen. So here's what would happen. Let's say the initial graph looks like this. If income increases, but price of Y stays the same, here's the new graph. We'll get something that looks like this. See how this is kind of stretched out? Like what I'm trying to show you is that this kind of moves out to the right as a result of higher income. Okay. Now, that does not change the height at which you decide to purchase X. So conversely, what would happen if price of Y increases, but income stays the same? Here's how the new graph looks. Here's the new graph. And this guy would look like this. So let's see if that's, I guess it would probably still come out just as far. But then do this. So let's see, is that saying that we will purchase, the price of Y increases, then we will purchase X sooner? Does that lower the, I'm trying to think if that makes sense if it lowers this mark point. So we could either have, so this is the original. This is what happens if income increases, but price stays the same. This is what happens if the price of Y increases, but the income stays the same. Will we purchase? We won't purchase more. Yeah, we won't purchase more X, but the breaking point lowers. Or no, the breaking point would increase. Let me a second to think about that. Yeah, the breaking point would increase. This makes more sense. Bye, Victoria. Okay. Yeah. So this is what you should draw if you want to draw it, I guess. Because I think that's the only way in which you can do that. How do changes in I and Y shift the demand curve for X? So the original looks like this. Let's just say, I guess you could say upward shift. And this would be a rightward stretch, I guess. I'll let you guys know if those need to be corrected, but that's what I would say about how the demand curves change on the basis of prices of Y increasing versus income increasing. Okay, let's look at E. What would the compensated demand curve for X look like in this situation? I'm probably going to skip that 2 for now because it probably ties into D. So I want to come back to D and E sometime later. Let's complete 5.1 for now. Okay, I'm going to jump over to 5.2. That's the next one we're supposed to do. Oops, hold on a sec. Yeah, 5.2. Give me a sec while I pull up the book. 5.2. Okay, whiteboard, got it. Okay. David N gets $3 per week as an allowance to spend any way he pleases because he likes only peanut butter and jelly sandwiches. He spends his entire amount on peanut butter and jelly. Bread is provided, blah, blah, blah. David is a particular eater. He makes sandwiches with exactly 1 ounce of jelly and 2 ounces of peanut butter. So these are perfect complements. 5.2. Perfect complements. Because the way he chooses to eat them, he says, I'm going to eat my peanut butter and jelly sandwiches in such a way that 1 ounce of jelly per 2 ounces of peanut butter. 1 ounce of jelly per 2 ounces of peanut butter. Okay. How much peanut butter and jelly will David buy with $3 allowance in a week? Cool. Well, thankfully we have the price of jelly. Price of jelly is given to be 10 cents per ounce. And the price of peanut butter, I'll say, yeah, B, is 5 cents an ounce. How much peanut butter and jelly will he buy with his allowance of $3 a week? So I equals 3. So I'm just going to reference my cheat sheet. These are perfect complements. We'll say J star equals, again, referencing that cheat sheet formula. Let me pull it up real fast. Cheat sheet. Perfect complements. And then this is the utility maximizing choices of A and B. I guess I need to actually set up the utility function, so that's important to note as well. We have min of AX plus BY. What are the values of AX? What are the values of A and B going to be for this particular function? So let's actually set up our utility function. U equals min of, so we can do J and 2B. Because you need, oh, I got that wrong. It should be 2J and B. We'll do a capital J. Capital J. So why do I have to, what seems to be confusing is that I did say 1 ounce of jelly per 2 ounces of peanut butter, and yet I'm putting a 2 on the J. Let's make sure we make sense of this. If I want to make a peanut butter and jelly sandwich, I only need 1 of these. Whereas I need 1 ounce of jelly. Whereas if I want to make a peanut butter and jelly sandwich, I need 2 ounces of peanut butter. So the peanut butter does not give me as much utility as the jelly does, or at least per unit of each component. So this gets a doubling effect. Or another way you can say it is as follows. You could say, rather than say 2J, you could say something like B divided by 2. This might be more accurate. But either one is fine. I'm going to go ahead and actually use this version for that matter. So utility is minimum of J comma B over 2. So just bear in mind that because I need 2 ounces of peanut butter for every 1 ounce of jelly, I need to divide the value of B in my utility function by 2. That means my value of A is 1, and my value of lowercase b is 1/2. Okay, now I can go use my cheat sheet for perfect complements. That would be B times I. In this case, I is 3 over B times price of jelly, which is 0.1, plus A times PY. And A was 1, and the price of peanut butter is 0.05. So we end up with 1.5 over 0.1, which is 15. Let's check it out again, but for B star, for peanut butter. This is A times I, so 1 times 3 over. The nice thing is the bottom is the same as it was for J star, so I'm just going to copy this down here. So this ends up being 3 over 0.1 equals 30. This checks out, by the way, right? Because we knew we had to purchase them in a 1-to-2 ratio. We bought 15 units of jelly, so 15 ounces of jelly, and 30 ounces of peanut butter. Okay, that's all part A once. Is that part A? Yeah, part A. Suppose the price of jelly were to increase to 15 cents an ounce. How much of each commodity would be bought? Okay, so we have to redo part A, but this time the price of, I'll just change this to B now. The price of jelly has changed. So we're going to have 1/2 times 0.15 plus 1 times 0.05. And this comes out to be a gross number. 1/2 of 0.15 plus 0.05 gives me 0.125, which then changes this. 1.5 divided by this answer is 12. And that's going to change this down here as well. I'll actually just, again, copy this guy down below. But now we get a 2.5 down here, which makes this answer 24. So this is your answer to part B. Let's look at part C. By how much should David's allowance be increased to compensate for the increase of the price of jelly in part B? This is very similar to a question we did earlier today about expenditure functions. So by how much should we increase David's income so as to bring him to the same level of utility as before? Is that how we're going to do it? By how much David's increased to compensate for the increase in the price of jelly in part B? Okay. Let's start by figuring out how much utility he had back when he was in part A. So in part A, David purchased or used, let's say purchased, bought 15 ounces of jelly and 30 ounces of peanut butter, thereby giving him U equals min 15, comma 30 divided by 2 equals 15, a utility of, this. So all I did to get this answer, to get this number, was I remember the old values of jelly and peanut butter were 15 and 30. So I just took those and put them here and here to get my value of utility. So there, at that point, he had 15. His utility was 15. This is what we're going to use in our expenditure function. So remember, I said that when we had a question like this before, this was like way back ago, like an hour, almost an hour and a half ago, probably about that long ago. To get this answer, I said use the expenditure function. So the expenditure function for perfect complements is E equals price of X, or rather U bar, times price of X over A plus price of Y over B. In our case, the utility we wanted to have him be at is 15. So 15 times, we need the new price of X. So the price of X we have now, remember, the original price of X, or the original price of jelly, is no longer 0.1, it's 0.15. So we'll put 0.15 here. A is still 1. The price of jelly is still 0.05. And the value of B is 1/2. When I crank this number out, I get 0.15 divided by 1 plus, whoop, turn my calculator off, 0.15 plus 0.05 divided by 0.5 times 15. This is $3.75. This kind of makes sense. What was his old income? His old income was $3. Now that the price of jelly has gone up from 10 cents to 15 cents, he's going to need a little bit more money to offset the increase in price. So he went from having to spend $3 to get a utility of 15 sandwiches to spending $3.75 to get the same utility as he did before. Part D. Part D asks, graph the results in part A and C. I'm not going to bother doing that. I'm not going to graph anything for right now. We can skip that for now. I'll just give you graphs later. In what sense does this problem? So we'll skip D because there's not enough room, and I don't want to make it room for it. Part E. I'll just send you out a graph later if I make one. Part E. In what sense does this problem involve only a single commodity, peanut butter and jelly sandwiches? Graph the demand for the single. Okay, whatever. Let's just talk about how this involves a single commodity. Because a peanut butter and jelly sandwich can only be made in these fixed proportions, we can condense the utility function u being min j comma b over 2 down to just u equals s, where s is the number of sandwiches made from the peanut butter and jelly we have. So this is the utility of jelly and peanut butter as if they were two different items. But since we're only using them in combination to make sandwiches, we can really just say, you know what? The utility can be thought of just being one good, u equals s, just sandwiches. Okay. Again, there's a graph that you might need to do for this, but I'll send that out later. Discuss the results of this problem in terms of the income and substitution effects involved with the demand for jelly. I don't know really what they really want from you here. I'll say this. For part F, because these goods are perfect complements, the change in price of any one of these goods, perfect complements. The change in price of any one of these goods will be completely due to the income effect and not the substitution effect. Why? Because these goods, well, again, these are perfect complements. There is no substitutability of peanut butter for jelly or vice versa. So the substitution effect is 0. There is no substitution effect with regards to goods that are perfect complements. Okay, so I guess that's the only thing they want you to say for part F. Okay, we are reaching a point where I'm hitting a break point, and like I said, this was going to be a 2-part video anyway, and I'm sure the people who are watching this video, or not watching, but at least in the room with me, are probably reaching a limit as well. I can probably do 5.5 and 5.6, and then I will record a part 2 later on, probably tonight or tomorrow. Okay, so 5.5 I believe is next. Yeah. 5.5. Suppose the utility function for goods x and y is given by u of xy equals xy plus y. This is an unfortunate one. So we have, this is 5.5. This is a really ugly looking 5.5. 5.5, this is an unfortunate one because this guy does not fit on my cheat sheet. You will not find a utility curve that is x times y plus y. You might start to say, well, Andy, don't we have this x times y Cobb-Douglas? Sure, but then there's also this random plus y at the end, so it makes it totally different. It's no longer a Cobb-Douglas production function. So that's something to take note, is that you will not find this on my cheat sheets. We're going to have to do a lot of this stuff by hand. Calculate the Marshallian demand function. So that's basically saying use the Lagrangian. So we're going to have to go back to using some first principles and say, maximize this guy subject to x times px plus y times py equals I. Okay, so here I go, Lagrangian time. L equals xy plus y plus lambda times I minus, I'm just going to copy this there. And I guess this would be a minus as well. Boom. Okay. I got to take the first partial derivative of L with respect to x. That gives me y plus lambda times negative px. I take the partial derivative of L with respect to y. That would give me x plus 1 plus lambda times negative py. And then I take the partial derivative of L with respect to lambda. But that, unsurprisingly, as always, just gives me my constraint. Okay, next step is to set all of these equal to 0 and solve the system. One of the recommendations I always give is solving for lambda in the first or second equation and substituting into the other. So I get y equals lambda times px, which if I solve for lambda from here gives me lambda equals y divided by px. Super handy because now I'm going to take this guy and plug it into this lambda. And this is going to give me x plus 1 plus y over px times negative py equals 0. I'm going to rearrange some terms here. I'm going to multiply both sides by px. So I get xpx plus px minus ypy equals 0. And if I actually, I'm going to add the ypy over to the right to get xpx plus px equals ypy equal, that's it, equals ypy. Okay. This gets me closer to an answer because I'm going to go back to my constraint, which says I minus xpx minus ypy. But instead of saying ypy, I'm going to note that ypy is this. That's ypy. So I'm going to replace ypy with xpx plus px equals 0. And I'm going to solve for x. I get I minus x, actually it ends up being 2xpx minus px equals 0. And then in an effort to solve for x, I'm going to add the px over to the right, or subtract the I over to the right, and I get, actually, you know what I'll do? Yeah, it doesn't matter. I'll say negative 2xpx. I don't like negatives. I hate negatives. So here's what I'll do instead. Rather than move the I and the negative, rather than move the I and the px, I'm actually going to move this term over to the right. So then I end up with I minus px equals 2x px. Then I'm going to divide by 2 times px. So I end up with finally x star equals I minus px over 2px. Okay. That gives me x star. Now I still have to go find y star. And this is where things get a little hazy and hairy. What I'll do is I'm going to delete all this stuff. I don't need this anymore. Don't even need this. All I really need is my budget constraint, which was xpx plus ypy equals I. But now I know the value of x. I have just found x star. I'm going to plug this guy in for x right there. So I get I minus px over 2px times px plus y times py equals I. One thing I'm going to note here is that I get an immediate cancellation of this px and this px. So I have I over 2 minus px over 2 plus y times py equals I. I'm going to isolate this term by itself by adding the px over 2 and subtracting the I over 2, giving me y times py equals I minus I over 2 is just I over 2. And then I have plus px over 2. So I took this I subtracted I over 2, and that gave me I over 2. I had a negative px over 2, and I added it to the right-hand side. It becomes positive px over 2. And then my last step is to divide by, actually, you know what I'll do is I'll combine this into one fraction. I plus px over 2. The last thing I need to do is divide both sides by py. So I'll just say this. I'm going to divide both sides by py. And that gives me, and I'll just do it over here. Y equals I plus px over 2 times py. And that's my y star. Boom. Okay. So I know how annoying computing Lagrangians were back from homework 1, but we had to do it there because this one was not on my cheat sheet. So sorry. Guess we had to do it by hand. Okay. Part A was calculate them and then describe how the demand. Oh, yeah, sure. Note that x star changes only as I and px change. However, y star changes as I, px, and py change. So that's worth noting. Part B says calculate the expenditure function for x and y. This should be, it'll be fine. So to calculate an expenditure function, you first plug x star and y star back into the utility curve, utility function. So what was our utility function? It was x times y plus y. So I'm going to plug x star and y star in for x and y. So this is going to give me I minus px over 2px times I plus px over 2py. And then I have plus y. So I have plus another I plus px over 2py. Now I've got some sad news for you because you're going to hate this part. I'm going to FOIL out. I know FOIL is that 4-letter word you don't really enjoy. You've got to FOIL out this I minus px times this I plus px. So if I distribute that, I end up with I squared. You could say plus IPX and then minus IPX. But the nice thing is that this is what's called a difference of squares, so that when I distribute the I minus px to the I plus px, those two terms in the middle just cancel. So there's no point writing them at all. What I do get, though, is a minus px squared. This is all divided by 4px py. That's what this entire chunk of terms comes out to be. But don't forget, I still have a plus I plus px over 2py. Okay. And this is, we're still, all we've done right now is create what's called the indirect utility function. So this creates the indirect utility function. So we're done with creating the indirect utility function. Indirect utility function. However, we were not asked to find the indirect utility function. We were asked to find the expenditure function. So we're going to keep plucking away. How do we do that? To find the, and this is something I said about a half an hour ago, maybe longer, to find the expenditure function from the indirect utility function, you solve for I. Now, looking at this indirect utility function, that's going to be kind of difficult. Notice that there's an I squared, let me try a different color here. Notice that there's an I squared term here. There's an I term here. And this one's being raised to the power of 2, and this one's not being raised to any power. And it's going to look pretty gross as is. So something's got to give. There's got to be some sort of magical thing we can do algebraically to make this work. Don't worry. I'll tell you how to get there. One of the first things you might want to do is say to yourself, well, notice that maybe in an effort to start solving for I might want to get a a single fraction, get a common denominator. So what does this fraction have on the left in its denominator that this guy does not? There's an extra factor of 2 because we have a 4 there, and there's an extra factor of px. So let's get a common denominator with this second fraction. What I'm going to do is multiply the top and bottom by 2px over 2px. In doing so, this gives me a new indirect utility function of I squared minus px squared plus 2pxi plus 2px squared, all divided by 4pxpy. And you might say, how does that help me? Well, you'll see in just a second. If you clean up my numerator a little bit, you get I squared minus, or rather plus, we'll say 2ipx, and let's just keep the same, 2pxi. Plus, we'll have a negative px squared and a plus 2px squared. That will become plus px squared over 4pxpy. Now, I might be thinking, I still don't see how this is any more useful because, of course, our goal is still to solve for I. But there's an I squared here, and there's an I here. But the numerator factors. The numerator factors into some algebraic expression. It factors into I plus px squared over, and then we're to keep the 4px of py. Now I can actually begin to solve for I. So I'm going to actually delete this junk in the middle. We don't need this anymore. And we'll drag this all the way over here. Okay. If I ask you to solve for I, what would you begin to do? The first step might be to take the square root, or not, multiply first by 4pxpy. So I get u bar times 4. I'll put the 4 out in front. 4 u bar px times py equals I plus px squared. Then I'm going to take the square root of both sides. So I get 2 times the square root of u bar px py equals I plus px. And then lastly, when I solve for y, solve for I rather, I get I equals 2 square root u bar px py minus px. And this is your expenditure function. Of course, one of the things I've said before is that to get an expenditure function, you are to replace I with E. So let's do that. Now it is an expenditure function. This is all the work that we did for part B. Actually, this is your answer to part B, but it started way back up here. We did all this work, including some deleted stuff, to get all the way to here. So part B is really tough. Part C wants us to use the expenditure function to compute the compensated demand functions for both x and y. Okay, that's easy enough. We're going to keep we need this guy still. To find a compensated demand function from an expenditure function, you take the partial derivative with respect to the price. And let's say for a particular good. So if I wanted to find the compensated demand function for x from an expenditure function, then I take the partial derivative with respect to the price of x. So let me make this look a little prettier. E equals 2 times, let's also do this. This is a giant square root. We're going to say 2 times u bar to the 1/2 times px to the 1/2 px to the 1/2 times py to the 1/2 minus px. Okay, now I have to take the partial derivative of this guy with respect to px if I want the compensated demand curve. So partial derivative of the expenditure function with respect to the price of x will give me my compensated demand function for x. What is the derivative of this guy with respect to x? So the price of x, I should say. This power of 1/2 will come down in front. So I have 2 times 1/2, say 2 times 1/2 if you'd like, times u bar to the 1/2 times px to the negative 1/2 times py to the 1/2. And then the partial derivative of negative px with respect to px is 1. After a little bit of cleanup, this is u to the 1/2, px to the negative 1/2, py to the 1/2 minus 1. This is your compensated demand curve for x, sometimes denoted x to the power of c. It looks like x superscript c. Let's do this whole thing again and find the compensated demand curve for y. So we're going to take the partial derivative of this guy with respect to y. You'll notice that a lot of this stuff will actually come out to be very similar. You'll have 2 times 1/2 times u bar to the 1/2 times px is still to the 1/2, but this time the power of y is now negative 1/2. And this term here, the px term, will go away because you're taking the partial derivative with respect to the price of y. So you will no longer have that px term, or at least won't even become the number 1. So we have u bar to the 1/2 times px to the 1/2 times py to the negative 1/2, and that's it. There is no further term because the px went away. This is your compensated demand function for y. All of this is part C. Okay, I'm going to do one more question, and we've been at it for almost, or a little longer than 2 hours actually. And like I said, this is part 1 of 2. So if you're watching this video now, if you're listening to this video now, there will be a part 2 that comes later, maybe the next day or 2, that tells you how to do the rest. So let me wrap up with 5.6, and then I will take any questions, and then we'll call it a day. Okay, we've got this table here, 3374. 3374. This is price of X, price of Y. This is the amount of X purchased, the amount of Y purchased. We've got 4266. And then 5173. And this is year 1. Year 2. Year 3. Okay. The question wants to know, is this behavior consistent? Come on now. Is this behavior consistent with the axioms of revealed preference? If you want a quick answer, the answer is no. Let's talk about why. It might help to figure out how much income is spent on these things. So here, this has an associated income of 3 times 7 plus 3 times 4, which is $33. It took $33 to buy these goods in this year. Let's do it again. For year 2, we bought 6 units of X, each costing, we'll say 6 units of X, each costing $4, and we bought 6 units of Y, also each costing $6. Sorry, 6 units of Y, each costing $2. There we go. And this is $36. And then next we have income equals. We purchased 7 units of good X at $7. 7 units of X, $5 each, plus 3 units of Y at $1 each, and this comes out to be $38. So income has increased from moment to moment. Let's make a few observations. One of the observations I want to point out is the bundle 7.4 is preferable to 7.3. That should be pretty obvious, right? Why is 7.4 preferable to 7.3? Because I have more of Y and the same amount of X. Now, you might not say strictly preferable, but you could say weakly preferable, and that's allowed. What do we mean by weakly preferable? It means either 7.4 is strictly better than 7.3, or we think of 7.3 as being equal to 7.4. But it's unlikely that we would think that 7.4 would be equal to 7.3. But we don't even need, for the proof that I'm about to do, I don't even need the fact that 7.4 is strictly stronger than 7.3. We could do weakly preferable, but we'll just say it's preferable. Okay, that's a pretty simple premise. Next premise is something like 6.6 is preferable to 7.4. The bundle 6.6 is preferable to 7.4 because I could have spent my money, my $36 in year 2 to purchase 7.4, but I didn't. But since I didn't spend my money that way, let's not say I. because this person has, and because this person, but since this person did not spend their $36 to purchase the bundle 7.4, they must prefer 6.6 to 7.4. Let's make sure that I'm not lying to you. Is it actually possible for this person to have purchased the bundle 7.4? Well, let's figure that out. If the price of X is $4 and the price of Y is 2, could I have purchased 7 units of X and 4 units of Y? Let's find out. 7 times 4, if I buy 7 units of X, each costing $4, that's $28 spent right there. Then if I go and buy 4 units of Y, each costing $2, that's another $8 for a total of $36. But I had that amount of money to work with. I had $36 in year 2, insofar as I was able to purchase 6 units of X at $4 and 6 units of Y at $2. I had $36, and yet, despite this, I chose the bundle 6.6 rather than the bundle 7.4, and so because of that, it must be the case that 6.6 is better than 7.4. Okay, this is the next stuff. The next part's pretty hard. With the money that I spent, or again, that this person spent in year 3, they could have purchased the bundle 6.8. Let's see if that's reasonable. So year 3, they had $38 to spend. Is it possible for them to have purchased 6 units of X and 8 units of Y? Let's find out. That would be 6 units of X at $5 each, plus 8 units of Y at $1 each. That would be $38. So they could have purchased 6.8, but they didn't. That's weird, because as you can probably guess, the bundle 6.6 or 6.8 is preferable to 6.6. So we've got this long chain of preferences here, right? The bundle 6.8 is better than 6.6. We said earlier that 6.6 is better than 7.4. And then we said at the very beginning, 7.4 is better than 7.3. So this seems really weird, because we have a situation where 6.8 is better than 7.3, and yet they purchased 7.3. So the answer is no. The behavior is not consistent with the axioms of revealed preference. There's a lot of steps here. Step 1 is that bundle 7.4 is preferable to 7.3. Obviously, if you have more Y than X, you're happier. 2 is a bit trickier. Let's put a star next to this one. 6.6 is preferable to 7.4 because in year 2, specific to year 2, I had $36. And I could have reallocated my money so as to purchase the bundle, the original bundle back in year 1. I could have done 7.4, but I didn't. I didn't spend my money to purchase 7.4. So it must be the case that I prefer 6.6 to 7.4. We're assuming that this consumer is rational. So that means they preferred 6.6 to 7.4 because they bought 6.6 over 7.4. The next step is, this is harder. This is another hard one. With the money that they spent in year 3, so that would be the $38 here. With the money we spent in year 3, we could have purchased the bundle 6.8. And just to quickly check, 6 times 5 would be 30. If I bought 6 units of X at $5 each, that'd be 30. And if I bought 8 units of Y at $1 each, that would be $38. The same amount of money that I spent in year 3. But I didn't choose to purchase 6.8. I chose to purchase 7.3. But this is where the fourth guy comes in, and this is where this guy ruins everything. The bundle 6.8 is preferable to 6.6. So I could have bought 6.8 in year 3, could have purchased 6.8, but this person purchased 7.3. But this is a contradiction, right? We know that step 1 told us that this guy's better. Step 2 told us that this guy's better. Step 4 tells us that this guy's better. I probably should swap step 3 and step 4, but whatever. Let's actually do that. let's move this. Oops, whoa. Let's do this. Move this here and move this here. And so I can say 3, 2, 1. Nope, nope, nope. Oh no. I just want to make that a 4. Okay, go away. Make that a 3. There we go. Okay, and then this guy is the hard one. Step 4 is the hard one. Okay. So step 1 says 7.4 is better than 7.3. This is kind of a no-brainer. Obviously, if I have the same amount of x, but I have more y, I'll be happier. Step 3 is also kind of a no-brainer. I have equal amounts of x, but I have more y in this scenario than I do here, so this is better. In step 2, I said that 6.6 was better than 7.4 because with the same amount of money, I could have bought 7.4, but I opted to choose 6.6. So we've got this long chain of events that ultimately says 6.8 is better than 7.3. And yet, with the money that I had in year 3, I could have bought 6.8, and I still opted to purchase what bundle? I purchased 7.3. This is a contradiction. So no, this is not consistent with axioms of revealed preference. Okay, that wraps up 5.6. I'm out of fuel. I'm out of steam right now, and we've gone at it for almost 2.5 hours now. So I'm going to call it a break for now. Like I said, I'm going to record the other half later on. Hopefully there won't be too much more beyond this. I know 5.9 is kind of a pain, but I know I said it'd be another 30 or 45 minutes, but it was looking based on the size of this homework and I know the difficulty of the problems that are yet to come. It's probably looking like another 1.5 hour video. So I'll make sure that goes out later on. But for now, we're going to call it quits here. If you have any questions, stick around and ask. Otherwise, I'll see you guys in the next video.